recursion, and in previous video we talked about tail recursion. We talked about we developed a function called as add vector, which adds all elements of an array. We developed a function called a multiply vector, which multiplies all the elements of a vector. So then we saw how to develop a function called reduce, which can iterate over and then perform the operation that we want it to perform. So this is a higher order function which takes a function and then performs that operation. So we could use reduce to either perform multiply or perform add. We also went in detail about how this add vector works, and in this video we are going to develop another version of add vector which is very similar to the iterative version. Now in an iterative version, what one would do is it would generally use an accumulator, something like a variable called sum. Then what you would do is which would be initialized to 0, and then you would take the elements one by one from the array and then keep adding it to the sum. Thus it keeps accumulating the sum. Now we'll see how to develop this as a recursive version, and once we develop that, we'll try to get an understanding of what does it mean by tail recursion, what does it mean by tail call optimization, and what does the compiler do. Let's get started. Okay, so the first thing is to develop a version of add vector using the concept of an accumulator. So let's do that. Okay, so what we do need is s, which is the array. Now if you see, what we want to do is we need to have an accumulator which is initialized to 0, and then we want to take the elements one by one and then add it to the accumulator. Want to be able to do something like this. So we take accumulator as an input which is initialized to 0, and the first thing we want to check is if it is empty. Now if it is empty, we just return the accumulator. Now why is this important? Now if you notice this, let's say our array is 1, 2 and 3. So we initialize the accumulator to 0, then we take 1, add it to the accumulator, then we take 2, add it to the accumulator, then we take 3, add it to the accumulator. Then when there is nothing else remaining to add, we need to return the accumulator. So if the list is empty, we need to return the accumulator which has already accumulated all the sum of all the elements, which is what we are doing here. That is why we need to take accumulator as an input, and then when we check if the list is empty, we return the accumulator. Otherwise, it's as usual, we need to destruct the array into the first element and the remaining elements, and now we need to recursively call add vector 2 on the remaining elements of xs, but we already have the element x. We need to add that to the accumulator so that it gets assigned to the accumulator that's passed to the next instance of the recursive call. That is why we perform x plus is equal to accumulator here. Now if you think about it, it's actually quite simple. If you follow this, what we want to do is we want to take accumulator as an input, initialize to 0, then if the list is not empty, we break the array down and destruct the array, and then we add it to the accumulator, and this value we need to pass it to the next one so that it gets added to the next element, and so on. So when everything is done, if the list is empty, we return the accumulated value. So let's see if it works. And the accumulator initialized to 0. That works. Now developing a multiply version is very easy. Instead of adding, we need to multiply. But then let's see how do we develop a reduce which is able to do this. So let's look at addvec. Let's follow this pattern. We need an s, that's an array, need an accumulator. So if the list is empty, we return the accumulator, so no surprises there. Then we break down the destruct the array as usual into first element and the remaining elements. Now at this point we want to recursively invoke reduce to, similar to the way we have done add to, on the remaining elements of the array, but we want to be able to perform an operation, and this is the operation that we want to externalize, because it can change, it can be addition or multiplication or anything else. So we take that function as an input, thus making reduce to a higher order function, and here we provide x and the accumulator value that we have accumulated until now. So this is nothing but it's adding x to the accumulator. If we supply the function which is an addition, if it's multiplication, it will do multiplication. Now let's see if this works. Reduce to, we supply an array, initial value is the initial value of the accumulator is 0. Now we need to supply the function x, and then we need to supply the function which will add the x to the accumulator. So we get x, we get the accumulator. Now we add x to accumulator. Let's see if this okay. Something went wrong. Let's see, function. Okay. So what I've done is I've forgotten to pass the function reduce to takes the accumulator. So this is nothing but the total value of the accumulator by adding x to it, and then the function as well. So if it's a bit confusing, what we're trying to do here is we are trying to say the new value of accumulator is nothing but fn, and then we pass the accumulator and the function. So now let's see if this works. Yeah, so that's fine. So now if we wanted to do multiplication, we would change the initial value of the accumulator to 1, and then instead of plus we'll do a multiplication. That works. Now let's go in detail about how is addvec2 actually working. Let's invoke addvec2 on an array of 1, 2 and 3 elements with the initial value of the accumulator as 0. Now at this point what it will do is it will say addvec of 2, it will break down the array, right? So the remaining elements are 2 and 3, and then what it's doing is it's adding 1 to the accumulator value which is 0. So if you notice here, the next step it has to do is to just return the value, right? So at this point, the function execution, at this point the current instance of this function that we are invoking, its execution is over, it just has to return. So at this point it has to, once it has computed it, it has to return the value. That's all, there is nothing else remaining. Now contrast this to what we had here. Here we still had another statement to execute, which was 1 plus then the value that we were going to compute, right? So now the next instance of add vec 2 is invoked with, so now we get 2 and 3 and we get 1. It's not empty, so it again ends up breaking down the array, which is 3. Now we got the value of the accumulator as 1. Now we are going to add 2 to it. So again at this point there is nothing else remaining to execute in this call. In this instance of the call, there is nothing else remaining to execute, it just has to return the value, right? So let's call this as point A, let's call this as point B. Now it calls the next instance of add vec 2 with an empty array. Now at this point it would add 3 to the plus the accumulated value of the value of the accumulator, which is 3, and it again invokes add vec 2 on this one with these as parameters. Now let's call this as point C. Now at this point what we have is, we check if the list is empty. Yes, it is. So here it decides that it has to return the accumulator, the accumulated value, which is nothing but 6. So if you notice, it has to come back to point C. It doesn't have anything else to do, it just has to return it, returns it to point C. It doesn't have anything else to do at point C as well, so just returns to point B. The next thing would be to return to point A, where it has again nothing else to do, so just returns it to point A, and ultimately that value is returned, which is 6. Now this is the key difference. Before we could say that the current instance of the function call is done before invoking the next instance of the function call. It had to save the statement to return to, because it still had something to do after the next call returns. So when the next call returns, it has to say, okay, now I have to add 1 to it, and that's true for every call here, which is in the version 1 of add vector. It had something, always it had to add x, it had something remaining to do. But in this version, the difference is that whenever it calls the next instance of the function call, it has nothing else to do, it has no other statement to execute except to return the value. Now this, in the terminology of computer science, is called a tail recursion. So formally, a tail recursion is nothing but a function call is said to be tail recursive if there is nothing to do after the function returns except return its value, return the value that is computed. Now you can go to this link to understand this concept in detail. So this is an introduction to what we mean by tail recursion. As in the other videos, we have tried to develop problems and we have tried to get an intuitive understanding of what tail recursion actually means. Now this leads to another concept called as tail call optimization. What is tail call optimization? As we saw here, there is no requirement for a stack in the sense that it doesn't have to save anything to the stack at this point because it doesn't have any operation to perform after the next instance comes back. Next instance of the function invocation comes back. It only has to return the value. Whereas in this version, it had to save the statement execute because it had to still perform 1 plus whatever value it computes after this call comes back to this. Whereas in this version, that's not required. So what compilers do is compilers do recognize this situation, and they don't save the stack frame for the current instance before invoking the next instance. So they just go ahead and invoke it. So this is called as tail call optimization. Now, what the compiler ends up doing is once it recognizes this that there's something is a tail recursion, is they just end up substituting with a iterative version which generally uses goto. Now how does that happen? So let's see what a compiler would do. Now let's say add vec 3 yes comma sac. Now it would still check if this is empty. It would still break down the array. Now at this point what it would do is it has to perform the initialize accumulator to 0. Now let's see if this was the case, and then add x to the accumulator and then assign s to xs, which is the remaining, and go to the beginning. Beginning is thing here. Go to the beginning of the execution and check if s is empty. Otherwise, add the value of the accumulator. The accumulator has to be defined here, otherwise it will get initialized to 0 every time. So this is what a compiler ends up doing. Now instead of using goto, just to see how similar this is to an iterative version, we can actually get rid of goto and develop this as an iterative version. So until our list is not empty, what we want to do is we want to be performing these operations, which is break down the array, get the element, first element, add it to the accumulator. Now have the accumulator initialized to 0, and if the array is empty, we just return the accumulator. So that's what it is. So that's what essentially the compiler ends up doing as well. It ends up converting a recursive version, if it follows tail recursion, to a iterative version. So this was an introduction to what it means by tail recursion, tail call optimization. Hope you have enjoyed the videos. I'll be coming up next with few more videos on the topic of recursion. Hope you are enjoying the videos. If you have not already subscribed, please subscribe to my channel. Thank you for watching.